In this video, we're going to talk about exponential growth. So you may have seen the formula for compounding interest, and that formula is P equals P naught 1 plus R over N to the NT. Okay, so this talks about discretely compounding interest, for example, in your bank account. So if you compound the interest monthly, the number of times would be dependent on how often you compound it. But what if, instead of compounding, every month or every week or every day, what if you compounded every instant? Every instant in time and move forward, you compounded your interest. Well, what would happen is you would get continuously compounded interest because you're taking a continuous limit. And so that corresponds to making n go to infinity because you're compounding infinite times every instant. So when we want to do that, we want to look at what happens when we take n to go to infinity. So we take our limit. Okay. So we're going to call this limit, well, it's our new interest, but we'll go ahead and call it, let's just say A for the amount that we're going to have. Okay, so we have A equals this side, and A is our continuously compounded principal. So you notice we have an exponent here with our n in it, and we're taking a limit with an n. So instead of having that in the exponent, let's take a natural log to get it out of the exponent. So we take the natural log of both sides. Then we have the natural log of all of this. So from our rules of logarithms, we know that we can break this up because there's a product. So we have the limit as n goes to infinity of the natural log of P naught plus the limit as n goes to infinity natural log of this part. Okay. So for right now, let's just focus on this. So that part is going to be limit natural log 1 plus R over N, the NT. Well, we can bring the exponent down because it's a log. So we have N, T, natural log 1, R over N. So what we can do is rewrite this, because what we have now is basically infinity times natural log of 1 plus 0. So we have infinity times 0. And remember, that's an indeterminate form, so we can use L'Hopital's rule. So remember, when we have 0 times infinity, or in this case, infinity times 0, we need to rewrite that to look like something else. We need to rewrite that to look like 0 over 0. And we can do that by saying this is really 1 over nt times the natural log of 1 plus r over n. Okay? So now we have 1 over 1 over infinity. So we get 0 over 0, because this whole part right here is 0. So now we can use L'Hopital's rule. Okay, so let's get a new tree. So again, we're now taking the limit, natural log 1 plus R over N, divided by 1 over NT. Okay, so again, we can use L'Hopital's rule, and L'Hopital's rule says take the derivative at the top, so we're taking the derivative with respect to n. So we say that's 1 over 1 plus r over n times the derivative of the inside here. Well, the derivative of 1 is 0. The derivative of r over n is minus r over n squared, divided by the derivative of the bottom is just negative 1 over n squared t. So let's simplify that. So the n squareds are going to cancel, so we're left with limits as n goes to infinity of, so the minus signs are also going to cancel. So we get r over 1 plus r over n, and what else are we left with? So there should be a t here. Okay. So now we can just apply our limit because we have an n here and an n here, so this is just going to go to 0. So we're left with RT. So now we can say that our original limit, we have natural log of a equals this limit plus the natural log of our initial principal. So now we can exponentiate both sides. So we get a is e to the RT plus natural log p naught. Well, that's the same thing as e to the RT, e to the natural log p naught. Well, e to the natural log of something is just that something. So we're left with p naught e to the RT. So for a continuously compounded interest rate, you get that the amount, or let's go ahead and call it p, it's just our continuous p, is our initial times e to the RT. Okay, this is a very important equation. So before we start doing an example with this, let's look at one property of this equation. So if I were to take the derivative with respect to time, I would get e naught r e to the RT, because you have to use a chain rule. And I can regroup this as r p naught e to the RT. And p naught e to the RT is just p. So another way to write this equation is what we call a differential equation. It's the equation with the derivative in it. So whenever you're given this type of equation, dp dt equals a constant times p, you immediately can write down p equals p naught e to the RT. So whenever you see this, think that. And that'll help you solve some of your problems in calculus, because this will show up. This shows up in exponential growth, it shows up in interest rates, radioactive decay, all sorts of things. So next we're going to look at actual problems using this type of concept.
Hi, so today we are going to solve this problem right here. It says a 100-gram sample of a material is known to have a half-life of 2 seconds. How much of the material will remain after 7 seconds? So, before we learn the equation, E is equal to P naught E R T. So for a half-life equation, we know that our final amount will be half of the initial. So in the problem before, it said that our time for half-life was 2 seconds. So we're first going to solve for R. And then we're going to take the natural log of both sides. And we get that for R. We know that the same thing for natural log of 1/2 is negative natural log of 2. We're just going to substitute that. divided by 2 is equal to r. So our rate is negative, which makes sense because it's decreasing. So we found our rate to be negative natural log of 2 divided by 2. And they want to know how much is left after 7 seconds. So our regular equation is that. So all I have to do is plug in the rate and plug in the time. And our initial was 100 grams. Sorry. And from there you can get a number. And that's it. So now we're going to do an example problem. The question says, what is the initial population if after 2 seconds the population is 10? So we have our information written right there. And this is our generic equation. So we are solving for P naught right here. So the final population is 10. And we're solving for P naught, E, and R is 0.1, as you can see up here. And our time is 2. So we're solving for P naught, so we're going to divide both sides by E time to the 0.1 times 2. And that's it.